Okay, so today we're going to be looking at a specific application that we've in the hybrid vehicle area. This is going to be we're going to use the BMW i3 as an example for analysis with our MotorSolve 6.0, which was introduced last fall. I would like to point out that some of the data was provided to us by Dr. Merwith from BMW, and also some of the analysis that has been done by Oak Ridge National Labs, Mr. Burse. Okay, so let's go on to having a look at a few of the features of the BMW i3. First, it's a permanent magnet machine, 250 newton meters of torque, peak torque, and at a maximum speed of 11,400 RPM. The voltage range of the battery is about from 250 to 400 volts, maximum current of 400 amps, and you'll see we also have 6-pole pairs and liquid cooled. And so here you can see an exploded view of the motor assembly. Now you can see that it's liquid cooled by the outside housing there. You can see the cooling system and the rotor in blue. Here's some data that was provided to us by BMW on this particular motor. You can see the torque speed curve and also the output power as a function of speed. And we'll be looking at this data and comparing it to some of the MotorSolve results shortly. Also, the efficiency map for the motor is provided for us, and we will have a look at some of that as well. And one little comment about this motor, it is particularly interesting in terms of hybrid vehicles because it has a very extremely high power density and a specific power. And so if you compare it from this table here with previous vehicles, you'll see that it is currently top of the list in terms of power density and specific power. So it's a very interesting design to look at. Just a comment here about some of one of the other presentations that I did recently, just so that you can also look back into it. If you want to find this presentation, you can also just send us a question here, and we'll be able to point you to where you can get this actual webinar. And it actually dealt with the generator portion of the MotorSolve in general. So we want to have a look at that. That'll be of interest to you. So let's talk a little bit about what Oak Ridge has done with this motor. First, they actually purchased a BMW i3, a 2012 i3, and actually benchmarked this design for the most part in 2016. They actually took the traction motor and disassembled it and did a whole bunch of things to get the dimensions and so on, determine some of the characteristics of it. So it's a 12-pole machine, 72-slot stator, and 36 coils in the stator. They digitized the lamination so that we could actually make models from it, and from that we actually converted that data into an actual motor model that was imported into MotorSolve. So here's a view of what the stator and rotor laminations look like. And this is an example of the actual DXF file that we extracted from the geometry that was provided to us by RNL, and which we used in MotorSolve as an import to actually create the final motor model. So this is the stator tooth, and this is the rotor, half a rotor pole, and you can see some of the features of the rotor, which is very interesting. It has 2 magnets, and it has some flux barriers and flux carriers to actually minimize the amount of magnet that's required to make this machine work. And this is the final MotorSolve model using those 2DXF files. This is just a view of the being the patent application for this rotor and stator design. Okay, so here we have the MotorSolve file. Essentially, this is at the point where we've actually entered the geometry in through DXF import, and we set some of these global specifications. For example, the supply voltage. Here we're going to use a 400-volt supply voltage, and set the rated current at 240 amps, and the rotor speed, and so on. In this case, was set to the rated speed was set to the maximum speed, but it can be set to let's say the corner speed, which would be more appropriate in this case. If you look at this on this page, we're seeing the actual specifications, the inputs for the stator settings, and you can also see a 3D view of that stator. And these are the rotor settings. Note that there's a slot skew to this stator. It's set to 1 full slot pitch, or 1 pole pitch rather, and you'll see a little bit later that this is going to be very useful because the actual stator the actual rotor for this machine is actually step skewed, and MotorSolve will actually take that into consideration when solving and analyzing this motor. So here are the characteristics of that motor. It has a 2-layer magnet arrangement. The reason for that is that to get a very sinusoidal induced voltage. Also, it has barriers and carriers to also increase the difference between LD and LQ. In other words, to get a very high saliency ratio. This will be able to extend the torque out to much higher speeds. It's got a very high number of pole pairs, 6 or 12 poles, and this is in order to reduce the yoke weight. And also, there was a particular attention taken to increase the mechanical strength of this rotor. So the rotor itself has 3 segments. Each is skewed with respect to the other, so to have a full half pole pitch. Once we've entered the geometry, the next section in MotorSolve will be to actually select the actual materials that form this motor, and this is the material selection page for MotorSolve. All right, and some more data that we're going to need. This data we're going to use for the definition of the stator winding. There's also some information about the mechanical and properties of the motor. What's particularly interesting is going to be the stator mass and the core mass and copper mass. These are things that we can actually calculate in MotorSolve, and we can actually compare it to see how well our model matches up with the actual motor itself. Number of stator slots is 72, as we said. There are 9 turns per coil. Each of those coils is formed of 12 wires in hand of 21 gauge wire. There are 6 parallel circuits in this per phase in this motor, which is kind of interesting. It has a full pitch concentrically wound with 6 independent neutrals, so wide connected stator. So here's the winding page of MotorSolve, and you can see here we've set the number of parallel paths to 6, and also we've set the wire gauge, and MotorSolve has an automatic winding capability, so it will automatically determine what is the best winding factor for this particular design. And so we choose. These are all the different balance windings. So we choose the highest winding factor winding, and we're going to use those. Once we've made those selections, you can see it also reports information about the winding itself, such as resistance, some inductance parameters, and so on, so that we can use that for testing or checking against the actual physically measured properties. And from this view here, you can see how the winding is laid out. So if you're more used to seeing how the winding is laid out, you can actually look at this view as well to see where each of the coils, which slots the coils are going into. And finally, for the winding, you also want to be able to handle the end winding in order to get the proper inductances and resistances. And these can be adjusted. For example, here what we've done is we actually changed the end turn length slightly by changing the gap height so that we can get the proper end winding resistance and therefore be able to better model this motor. And finally, when you have all this set up, you can actually go down to the bottom and see what the design information on this motor is here, and you can see several things that are of interest. The first is that we now report what is the skew for the zero cogging torque. This can actually be calculated, and we actually calculated directly based on the geometry what that skewing factor is. And in actual fact, that's exactly what was done in this case. We used a one slot skew or one pole skew actually since it's the rotor that's skewed, and also some of the masses here. If you were to compare these to what was reported from BMW, you'll see that these actually match up quite well. Okay, so now we've got the geometry set. We've selected the materials. We've changed some of the parameters. The first thing we want to do is we want to look at what the flux densities look like in the machine, and we'll use the open circuit flux field to do that. So we'll see what the magnet flux is producing in the circuit, and secondly, we'll look at what the back EMF looks like at the maybe at a couple of speeds. So here we have the open circuit field solution. You can see that the maximum field is quite low. It's somewhere in the vicinity of 1.2, 1.3 Tesla. We're not getting much saturation in this machine. So this machine is operating in a fairly linear range. So it'll be interesting to work with. Here we have determined what the back EMF was for this particular for the corner speed, which is set to about 4,500 RPM, and this turns out to be about 200 volts peak for this machine. At the 11,400, the peak voltage is about 510 volts in that case. So obviously, if we only have 400 volts, we're going to have to use field weakening in order to be able to make this machine work all the way up to that speed. Okay, so we've done our first testing here. Let's have a look at some of the details about the motoring. So we'll look at some motoring simulations. And once we've done that, we'll go on and have a look at some of the capabilities of this motor in terms of generation. We don't have too much data for the motor yet in terms of what it can do in a generation mode or during braking, regenerative braking. So we'll sort of display how we can actually use MotorSolve to get that kind of information. Finally, we'll compare some of these results with what was obtained from BMW and also RNL. All right, so the first thing we may want to do is to have a look at how much cogging there is in this machine. So we just select the cogging torque analysis and run the analysis, and you'll see that since this rotor skewed, one pole pitch has 6 stair steps for the rotor cores and magnets. And you can see that we calculated an identically 0 cogging torque. So there's really no cogging torque for this design. And that was a very clever way of building this motor. All right, now let's have a look at a little bit the how this motor operates under in real operating conditions. Now, MotorSolve has 2 different modes of PWM analysis. It has a current hysteresis and also a space vector PWM. We'll be using current hysteresis PWM for this analysis, and we'll see how well it performs under that type of operation. So what you're seeing here is the irregular waveform is the actual waveform under PWM, so it's not purely sinusoidal. I mean, we can make that closer to that by changing the hysteresis bandwidth, which is shown by the upper and lower sinusoidal waveforms, and what we can work with that and see how well things will operate. Now, as I said before, we will be wanting to use field weakening, and that's going to be done by changing the advance angle, the current advance angle, and we'll see how well that happens in the following slides. So let's have a look at a few different advance angles, and we'll look at several points. Now, we've split up the torque speed curve along 6 load points. So here we're going to look at both the output power and the torque at those various points. And these are the actual measured values that we'll be comparing them to. And we'll now look at what happens. So let's have a look at what happens and how current advance angle actually helps us to field weaken. The red curve here represents the total torque of the machine. The green curve corresponds to the permanent magnet torque produced by the machine, and the blue curve corresponds to the reluctance torque produced by the machine. So if you were to move this cursor along this as a function of advance angle, you could find a point where you could find a point where you can get perhaps maybe maximum reluctance torque, or you can choose to find out what the values of the reluctance component and the permanent magnet component of the total torque occur. So this is a very useful curve especially when you know what advance angle you want to look at, or have an idea approximately where you want to operate, what advance angle you might want to operate at. So let's have a look at what happens at maximum speed here. Here we have a 62 degree current advance angle, and you can see now we have about 90 Newton meters at that speed, at that advance angle. If we change it to 57 degrees, you can see the actual average torque actually goes up to more around 117 or so. And at 56, we're up to 160. So it's changing quite rapidly here. And so we'll show you a few more. So this is at 52. We're now nearly at 200. And at this advance angle, we're actually at 250. So what we've done in the end was we've selected an advance angle, which in this case we chose 70 degrees, and we plotted the torque speed curve and the output power versus speed. And you can see that the corner speed of this machine is somewhere around 5,000 RPM, and also and the maximum output power occurs somewhere around there. And let's compare that to what we had from the actually measured results. So I've reproduced those 2 curves on this chart, and the dots represent the actual measured data. And you can see that we're actually modeling those curves quite well with MotorSolve and with a single current advance angle of 70 degrees. Some of the other quantities that can be useful and that are pretty typical that, for machines is you can, for example, look at the KT and KE values. Some of the other quantities that are also useful: no load without any advance angle, the LD-LQ values, XD-XQ values, and also LQ over LD, which is the saliency ratio for this particular machine. This particular machine actually has a very high saliency ratio of about nearly 3. It's 2.8, so it's a very high saliency ratio, and that's the reason why you have a lot of reluctance torque. If you have in surface magnet materials, surface magnet motors, for example, the saliency ratio is basically pretty well 1. So here we have we're using the reluctance component quite effectively. Finally, this is the calculated efficiency map for this particular motor. You can see that there's quite a range by the orangish color, the darkest orange color, that where the motor is quite efficient, which has a very high efficiency, over 97%. So the machine is quite efficient over at the high speeds. All right, let's have a look a little bit at the generation capability of this motor. We'll also be able to, since we don't have a lot of detail on the generation capability, we'll be concentrating more on what kinds of analysis that we can do with MotorSolve on a generator using this particular machine. Now, the BMW motor, the BMW is used in 2 versions of the i3. There's the pure electric, where the only generation mode is regeneration during braking. But there's also a range extender version, which also includes an induction. It actually uses a fuel-driven motor to actually generate electricity for the electric motor itself. In this case, there's active transistor voltage regulation, and we'll show some results for that kind of analysis. Okay, so generator loads can be analyzed in several ways. We can look at the short circuit capability of the generator. In other words, what is the maximum current that this generator can produce? We can look at this motor with passive impedance loads, and we can also look at infinite loads such as the grid, so the connected directly to the grid. And what we'll be more interested in here is going to be the diode rectification, such as in braking here. We'll look at a little bit of that. So here's a typical rectifier circuit, and our DC battery here is what the battery voltage for our motor. So some of the quantities that we calculate is the phasor for the phasor diagram for this generator. Important thing to note about the MotorSolve is we also can provide you with the motor phasor diagram instead of the generator phasor diagram. It's slightly different, and you can also get that from MotorSolve. Here is the torque versus load angle curve. This is more interesting for cases where you may have a portable generator connected to a grid or something like that. You'll be wanting to use this kind of curve for analysis. The output power versus speed is also a quantity that, and this of course is also used as a passive load or an impedance load. Regulation curves. Regulation curves, again, we're not going to be using this for the hybrid motor because this is more for grid-based, so for hooking up to a grid system. And what we could use here is the voltage versus current curves. So this is the voltage versus several different impedances. So we're looking at the different impedances. The impedance, of course, here can be it's pure impedance. It doesn't have to be just a resistance. It can also be, we're looking at an inductive load here for the output of the generator here. So here's at 48.4% rated speed, and this is at 100% rated speed. So you can see where the maximum voltages are for this generator, depending on the output impedance that it's connected to. All right, so let's get on to looking at what happens in the BMW itself. For that, we're going to be using what's called Rotor model generation. And there's several display modes that we have available to us for that. We can actually look at the waveform. We can look at the time averaged quantities, so the could be average power, things of that nature. We can also look at the harmonic. We do a harmonic analysis of the waveform, either to get its amplitude and or phase. And we can also use the phasor diagrams, as I've shown you before. Each mode that we look at has its own set of quantities that we look at, and the load type can be either impedance, which is impedance, or having a diode bridge. We'll be looking a lot at the diode bridge, but we'll also look at the impedance here. So this would be like in the more like in the case of the i3 with the IC motor. All right, so let's first start by looking at what the back EMF waveform looks like again. So here we have our waveform. We can see that what the maximum voltage is just under 500, under 400 volts here. So at the rated speed, which is about 4,500 in this case, we don't have much of a headroom here. So it's actually below the battery voltage. So we're not going to be generating any kind of power back to the battery here. So here we're looking at those voltage versus current curves that we were talking about before, and we've selected certain impedances to have a look at what the maximum output power is for at which impedance we get the maximum output power. So we can look at these charts and have a look at that. These are the two different speeds here. So it's at 48.4% full power, or full speed, or at 100% full. And this is the data that is actually stored, that's used to display those charts, so we can actually also look at the data and use those in other types of analysis if we want, or to actually chart them externally as well. And in this view, what I've done here is set up the basically set up the motor in generation mode, and I'm using a battery voltage of about 400 volts. So that's what the rectified voltage is here, and we can see that it doesn't produce any voltage until it reaches about 5,000 RPM, and then you can see the current and the output power going up and going back into the battery. Of course, this is just assuming that we don't have any kind of boost or anything like that, so that the voltage that we don't actually have any voltage boost. So we actually have to have a voltage greater than the actual voltage of the battery.